Hello, everybody. Welcome to the Student Chapter Seminar Series. Today we have Juan Diego Toscano from Brown University. Um, Juan is a PhD student in applied mathematics at Brown University, advised by Professor George M. Cardiadakis. He received his BS in mechanical engineering from Universidad de las Fuerzas Armadas. His research focuses on developing reliable and stable machine learning methods to study complex physical systems that resist traditional analysis. To this end, he designs new architectures and optimization methods for scientific machine learning with applications to chemical reactors, turbulent thermal convection, and biofluids. More recently, he started exploring agentic systems for scientific discovery, in which teams of agents reason across ML, classical solvers, and particle-based simulations to propose numerical methods and surface analytical insights such as well-posedness results and exact solutions. Juan, you have the floor.
Hi. Thank you so much, Valerie, for your kind introduction, and thank you everyone for your time. It's really an honor to be here. Um, uh, well, as Valerie was mentioning, my name is Juan, and today I'm going to talk about our recent study called GRAFT-ATHENA, which is self-improving agentic teams for autonomous discovery and evolutionary numerical algorithms. First, what is GRAFT-ATHENA? Well, GRAFT-ATHENA is an agentic system that learns from experts and from online documentation. It can create maps to learn from past experience and induce informed rewards. It can implement high-order solvers in one shot. In this case, we have like the Apollo mission from a report from 1968. It modeled like in a single step. It can achieve near machine precision in canonical physics information learning benchmarks. It can solve inverse problems and detect closeness and propose regularizers, and also can propose new numerical methods with spectral convergence. Um, Before diving into what about how GraphAthena is constructed, maybe we can stop to think what it's missing for human level intelligence. We see that these agentic systems start to get smarter and smarter every day, every month. But what is the main difference between them and us? And this question have been posed many times in the past since the introduction of artificial intelligence. And one of the answers came from Professor Pearl in 1988, and he said that the main obstacles are adaptability, explainability, and understanding causation. And he took it one step forward and saying that actually the hallmark of human cognition, in this case, he was referring to understanding causation, is a necessary though not sufficient ingredient to achieving human level intelligence. So um, he proposed a thing that it's called the ladder of causation, and then this is ideally in the way how humans would work in some sense. Like in the first level is seeing, like making association. The second one is like trying to do intervention and answer the questions like, what if I do this? And the third level, which is the imaginary level, is when we go to the counterfactual. And then this one is where the big discoveries come from. Like in this case, for example, one good example would be Einstein's, as he quoted, like his happiest thought of his life when he imagined like a guy falling from the roof and he figured out that he would not feel gravity. So then he found out that that's how he discovered relativity based on only on his this kind of thought experiment. Yeah, this is important because this is a one-way ladder, which essentially means that you can only, if you have a system that describe this imaginary world, you can this system would also help you to describe this intervention work and the association work, but you cannot go all the way around. Actually, Pearl put it in another way, says that systems that are only based on associations, they are prevented from reasoning about novel or causal explanations. And why is this a problem for us is because if we think into the association level, this is the way that you model is like the probability of y given x. And this is essentially the same thing that we do for LLMs, right? It's like the prediction of the next token given on the past. So LLMs, they are smart, but essentially they live into the association level. And Pearl did like a kind of like a rigorous analysis, and then you can show that you cannot go to the upper levels if you only live in the first level. This latter also explains why agentic systems have become more popular and why people like them a bit more is because they essentially live in this intervention level. like they have the ability to interact with the environment and to change things to make decisions, right? However, for the counterfactual level, we still don't have an answer of how to actually solve it. And so ideally, the new agentic systems would try to include tools like build this setup to try to go to this third level. Maybe one way to start, we can like take a look into an L2 agentic system. Like remember, this is the interactive level. And for this case, we're going to use one of our examples, which is this Athena, the first Athena paper that we had. But in general, all these L2 agentic systems follow some kind of path. They will try to solve a problem. So when you get a problem, essentially they will try to mimic the way how we approach problems. So when you get a problem, you will try to study it. You will generate a plan about how to solve this problem. You will try to implement it, and you get some kind of code. You get some observables. From these observables, you analyze it. You say this problem is good or is bad. You assign a reward, and then you decide what to change, right? So since you what to move to the next, how to modify my plan to solve the problem in a good way. One way to model this is using a thing that are called contextual bandits. And the reason why we do that is like it gave us a metric. And this metric is called the regret, and essentially just measures every time that we go through this loop, how far are we from an optimal answer? So we know that this optimal answer lives in some kind of a space of solutions, and how far are we from that solution as we iterate on into the system. It gives us conditions to learn, and it gives us a goal. Essentially, tell us that this regret has to be sublinear, which essentially that as you go farther in time, as you iterate, you start to get closer and closer to this optimal solution. One of the things that it's important in this modeling is that it's based on this thing that is this pi, which is the policy, and the policy essentially tell us once we get a result, how do we modify the plan? So essentially, it's a probabilistic map between actions. So it's like I see what happened with my previous plan, my previous selections. I see what are my observables. I analyze what is happening, and then I think how to solve the problem. And this is the important part where we need some kind of understanding of causation and causation. One way to realize this graph is just replacing the humans here with an LLM, and then you will have an agentic system, and then you will have some foundation on what to encode. However, as we mentioned in the previous slide, normal LLMs will not have this kind of causation understanding of the world. So one way to address this thing would be, for example, to try to give expert knowledge. So you tell these agents how to think, like when you see this type of problem, how to solve it in some sense. And the general idea is like that's how can you try to bridge the gap in some sense. And if you take all of this together, you take this map and then you put a lot of agents in place of the humans, you end up with a system that looks like this. And this is what we call, in this case, Athena. And you may see that it's quite similar to several other agentic systems that also live in L2 that follow a similar pattern. Now, maybe one of the questions like, does this work? And the answer is it works quite well, especially when you encode this expert knowledge. Like for example, we asked Athena to solve a 2D implicit Borger's equation, and this is a hard problem because you cannot use like a normal naive numerical method. If you use a normal numerical method, this thing is not going to work. It's a complex problem, and my hope was that Athena would be able to come up with the traditional way of solving it. I don't know, using finite volumes, this window scheme. However, Athena figured out that this was a 2D problem. However, if you rewrite it, you can express it as a 1D problem. And if you express it as a 1D problem, you can solve it using a thing that is called the method of characteristics, and you can solve it exactly, which essentially means that you can solve it with no error, which is something quite interesting. And if you have been working with agentic systems, with this type of hyperbolic conservation laws in the past, you may complain. You may say, okay, you can use the method of characteristics up to the shock, but after the shock, you cannot use it because you don't have a unique, strong solution there, right? And Athena knows that, and actually, if you run it 5 times, so after the shock, you have to find a thing that is called the entropy solution. So if you run it 5 times, Athena finds 5 different ways to obtain the entropy solution. Um, Another interesting problem is like you can try to trick it. You can try to ask it a problem that should not be solved. For example, you ask it to solve using pings and implicit 1D Borger's equation, and for the same reason as before, like implicit Borger's equation do not admit strong solutions, but traditional pings look for strong solutions. So this should not be a problem that should be solved with pings. And this is the advantage of having like these teams of agents interacting with each other, but because you see that the first, when you propose the map, when you propose the plan, the strategy is proposed using like a strong form ping solution, but then immediately the critic rejected and says that this doesn't work, and actually ask it to use a viscous surrogate. And then it tries to solve it, but it blows up. And then the advisor agent, again, because remember all these agents have like this expert knowledge, it's able to identify that no, maybe you want to include some type of entropy conditions. And then you see that when you try to solve this problem, after 22 iterations, you get an error of 10 to the minus 4, which is 0.0001%, and 0.01%. And why is this important is because the previous human benchmark for this was like 10 to the minus 1. So you get almost 3 orders of magnitude when you let them think in this structured way. You can repeat this exercise for many other problems. And in this case, we tried to see if it can uncover other analytical solutions besides the implicit Borgers, and it actually found for 5 other benchmarks it could. Also for other numerical methods, it did quite well. And for pings also did it quite well. In all these cases, they achieve really low residuals. So yeah, and if you analyze the reward, which is what we're looking at this first row, you see that the reward tends to increase, which is good. It means that we are getting better and better. This is structures, thing that we call like a sub-martingale on the reward. And if you try to analyze the regret itself, you see that this regret follows this sublinear pattern, which is the theoretical um, uh, limit that how we define the system. And so it means that Athena it's able to learn. So if you have a system and then you encode the conditions to learn from the contextual bandits, you can actually get an agentic system that can learn. However, even though Athena can learn, it cannot remember. For instance, you see that in all the cases, especially every time that you start a new problem, you have to start from zero. Your reward restarts. And even if it's a similar problem, for example, here you have Poisson and Helmholtz, and if you solve that problem, you know that both of them are quite similar. So when you solve a problem, if we are humans, we know every time that we solve something, we learn. But these agentic systems do not have the ability to learn for now. And this is not the only problem with Athena, it's a problem of formulation. That's why, for example, many other papers that you may have seen there, like for example, they run their agentic loops for 100 or 1000 times, and then they rank them and they choose which one is the best. And that's how people is doing things. But so it's essentially, it's a problem. In our case, it was like a framework limitation because the policy is fixed. But mainly it was because we don't have a mechanism to absorb experience. We don't have a way to structure information in somehow like a nice way. So it's a representation problem. So how to move forward is like a question, and maybe one way to try to solve it is like maybe taking one step back and think, how do humans do it? Like how do we tackle this type of problems? And let's assume that we have a simple problem, like say an agentic system that tries to plan our morning routines, let's say to go to work. And if we think how would we do it away, maybe one thing that we would consider is like, what is the day of the week? Maybe it's Monday, it's Tuesday, Saturday, Sunday. It's raining or it's not raining, and maybe then the thing that we want to figure it out is like, okay, where are we going to have breakfast? Are we going to take our bike? Are we going to take the car? So essentially, this kind of like toy example, like help us identify that what we're asking our systems is like to create a map from problems to methods. So essentially, if it's Monday and it's raining, maybe I will have breakfast and I will take the car. And actually, this this description is natural and it can go to other fields, for example, let's say in PDEs, like let's say you can put in the categories like the dimension, it's a forward or inverse problem, and then your map will tell you, okay, I'm going to use a ping, I'm going to use a sort of spectral method, what is the number of collocation points? And so actually this surface something that this is natural, the natural way how we describe problems. Like we define categories, like, and then from each one of the categories, you would choose one option, one feature. So yeah, yeah. So actually this defines something like a cleaner map. And actually, if you can, we can write it in a better way. We can write it as a direct acyclic graph. And here we can see the nodes that we identified. For example, in this case, we're going to explore for the method space. We're going to, okay, in the morning, I'm going to choose, if I have breakfast, I'm going to choose my transport. I'm going to choose the type of clothes that I'm going to wear today. And then in each one of these selections, we're going to choose one. For example, I can have breakfast or not. I can take my bike off my car or my car. I can wear formal or casual, and I can wear my helmet or not. And this structure, you can see that essentially this surface something else that actually the decisions are not like deterministic. This is in somehow like you have some source of randomness. For example, if it's raining, well, the probability of choosing the car will be higher than the probability of choosing the bike. And then out of nowhere, you see that if you replace these blue arrows with some kind of probabilities, then essentially you are constructing the map, right? So you're generating this probabilistic map from methods to problems, which is what we're trying to look. And another interesting thing about this is like this simple structure already contains all the information from the action space. And in a specific observation, let's say I have breakfast, I take my bike, and I wear casual. It's just selecting one node of this graph. So essentially all the problems, many problems can be encoded in this kind of a small representation. Okay, so then that would be one way to tackle the representation problem. But there are other issues, like for example, if you try to do it this naively, okay, we understood that we want the probability, so we can try to construct like a transition matrix, and then we see that each layer of the transition matrix will be, for example, we'll have n squared with the number of elements. For example, we have 2, 4, 6, 8, so it will be an 8 by 8. And then every time that we add some kind of dependencies, for example, I know that if I take my bike, I have to wear my helmet. Well, this makes the size to grow exponentially. And the problem with that is that for real problems, you cannot even fit it on memory. So one way to deal with that is like to try to identify decision levels, which is again something natural that we do. Like we don't take all the decisions at the same time, but we take the ones that are independent first, and then we take the decisions that depend on the previous level. In this case, first we define that we're going to take the bike, and in the next level we define that we're going to use our helmet. Yeah. Actually, you can make if you restrict your action space to these three types of connections, like either they derive it into categories, and in each feature you derive it into a specific option that you have. In other words, into these green and blue arrows, and then the dependencies work like this. Actually, you can be a bit more formal, and then you can prove that you don't lose any information when you do this transformation. And okay, and now we have something that it's in some way learnable. Okay, now if we take this one step forward, we actually can project this graph into some kind of tree, and then if we do it in a mindful way, we can actually get injectivity, which essentially means that the action space is the blue arrows, and then these yellow or orange arrows will be the specific selection of the method, which essentially means that each method that you select will have a specific space into this unit cube, and not only in the cube, but also in its shadow. And this is the thing that we call the fingerprint. And again, this sounds restrictive at the beginning because you're only allowing three types of connections, but this is more general than we think. And actually, using this description, you can generate like a methods tree. And in this case, this tree already encodes all the information from a commercial software. Like, for example, in this case, we have Nectar++. These also have Trixie. which are spectral element solvers for the numerical methods tree. And you can do something similar for the problems tree. And what do you have on the left is the actual DAG of some kind of the problems and methods that the system is solving, right? And then again, when you take the shadow, you can get this fingerprint. And this essentially tells us, okay, Athena will just try to take this fingerprint and identify what will be the right method. This is quite interesting because the moment when you get this uniqueness, this injectivity, you can start to compute distances, and you can start to do things like this. For example, you can do things like PCA, and then you can identify for each method, like you can generate this map of, for example, methods and problems. And in this case, for pings, I'm going to comparing the laws. And then, for example, you can see how they gather. For example, for 1D problems, for forward problems, your laws can be almost machine precision, but for inverse problems, it can only be 10 to the minus 3. And in numerical methods, you can do things similar, some similar things for the wall time, the time that you take to solve the problem. And you see that they gather properly. For example, in this case, we have incompressible problems. And for the DPD, which is the dissipative party called dynamics, people use it for many things, for modeling, all the way from modeling the blood to modeling the planets. You can see that you can analyze other things, for example, as the number of atoms. So, and then you can code these problems nicely, right? And then you can imagine that when you get a new problem, let's say that you get a problem that is here, you can somehow figure it out what will be your loss into this system. Okay, maybe let me clean my screen. Okay, so once you have this thing in place, sorry about that, you can define what is the full structure of GRAFT-ATHENA, right? So the first part will be an expansion team, which be something that in the way that you're going to construct these graphs. And since this is a natural way of describing problems, like defining categories and optionally decide each one of those categories, most of the commercial software are already written like that, and you can have a team of agents interacting with the documentation or with experts of papers. They can extract the DAGs and the hints, and then they can embed it into the overall system. And then that's how you construct it. It's quite straightforward. And then when you have a new problem, you can have a formalization team. You will have a user interacting with a formalization team who's going to identify the problem, try to simplify it, see that it's well posed. Once you get the problem, you can encode it into the graph using some encoding team that is also a set of agents, and then you will get this problem fingerprint. Again, since you actually can have this metric space, so you can compute where it's the distance between the previous problems that are in that are in the system. What are the closest problems? You find what are the closest methods, because this is saved in the memory. And all this past information can come from here, from talking with experts or from previous papers, right? And then from that, you can get this probabilistic action space, which is nothing more like just averaging the information of the closest methods of the way that you solve the closest problems, right? And then when you have this action space, you can use a strategy team to sample the method, and then you can just do the loop that we talk into the previous system, and then you can keep repeating until you satisfy your requirements, like until your problem is good enough. And something interesting here is that you can also save the bad information, so you can also save the places where the system broke, things that didn't work that well. So essentially, this system, this type of memory, allows you to save both the good information and the bad information. So this system can learn both from the good things and also from its own mistakes, and it can use it to guide the next decisions. And maybe this will be a bit more clear in this example. Let's say in this case we're trying to solve this viscous Borger's equation with the ping, and then we find what are the closest problems. And in this case, this one is the implicit Borger's equation that I showed a few minutes ago that normal Athena solved. This problem 2 is Allen-Kahn equation. This problem 3 is KDB. All of them are hyperbolic conservation laws. That's what the model finds they are the closest ones. This Hakar for distance, you can think about a percentage. Maybe this is 60% closer to the target problem. And then you see that from each one of these past problems, you actually have a corresponding method. You know how to solve it, right? That's because you solve it on the past. So now that you get these methods, you can just average them. And it's a little bit of noise to get this map. So what you have here, the light colors means like lower probability, and the higher colors means higher probability. So things that you can observe here directly, for example, you see that all these problems have this pattern here, and so this part is darker from the true action space that you're going to use to sample. And this works quite well, for example, in this case for this case of the once you remember, once you have this merge prior, when you have this action space, you just sample and then you try to solve the problem iteratively. You see that for the viscous burgers, you get really good performance. The relative error is lower than 10 to the minus is 10 to the minus 9. And then you see that when you compare with the normal Athena without the graft, you see that it beats it. But and the interesting thing is not how did it beat the normal agentic system, but why? And the answer is here. You can see in this region that in this part, the relative error is relatively high. And the reason was because I told you this problem was the implicit Borger's equation that I talked a few minutes ago. And in this case, the agent found out that it's good to do a thing that is called viscous continuation or Reynolds continuation, which essentially means that you will not solve the problem directly, but you will solve a simpler problem first. And for the implicit problem makes a lot of sense, but for the viscous Borgers does not make much sense because this problem should be simple enough to solve it directly. And that's why the normal Athena is trying to do that. And that's what I would have done directly, right? But this thing, since it found this common problem, it figured out that this helps. And in this first stage, it's solving the simpler problem. And then after the simpler problem, it solved it to the actual complex problem. And then that's how it fits it. So essentially what we're showing is that having this ability to learn from the past experience from closer problems, it's helping the system a lot. And you can do it for more examples. For example, this is some of the canonical benchmarks in physics for machine learning. All these cases, the PDs, the initial conditions are all the same. And then you can see that in the mean squared error of the loss, you get almost machine precision. And you beat both the humans and the agentic benchmarks. And you can see that the humans, the closest ones, were actually quite close. They get 8 to the minus 9, but you get 1 to the minus 9 with that trick. And also for the other ones, right? So it's, of course, this information from sorry about that. This information from the best human is part of the thing that you fed into the system above. So they are building on top of that knowledge. That's why they can go that low. Okay, now maybe I'll go to another example. This is the case of the thing, the Apollo mission. This is in a different field. This is in classical numerical methods. In this case, what the system is trying to do is trying to model the re-entry of this Apollo mission, the Apollo capsule that went to the moon and when it was coming back, the re-entry to the atmosphere. And then you see that again, we can get the target problem and we get the closest problem, which is 71%. And then here you can see the merged prior and how. So this is the thing that you're going to, again, you find the closest problems, you select the corresponding methods, you average them to get the action space, and then you sample from there. And the agentic system takes care of everything, actually. Once you identify the method, it takes care of the meshing, it takes care of the mesh refinement, it takes care of the mesh quality control. And actually, in this stage, they start to do really some things that are quite interesting. For example, they identify that under resolution will crash positivity, which essentially would mean that your solver will blow up because your pressure will become negative and your pressure goes in within a denominator or something that has a square root too. So then your things will blow up. Yeah. So when you solve this, these are the results that you get. This is at Mach 10. This is a really complex flow. What you have in the first row is the density, the second one is the Mach number, and the third one is the like Schlieren imaging, which is measuring of the density gradient. Yeah. Another problem is in this case we're asking it to solve an inverse problem. Like in In this case, you will have some this mice which is alive. You will inject some particles into the neck of the mice. These particles are going to go inside the brain. And then you're going to do a thing that is called two-photon microscopy. And then you're going to identify these particle tracks in some kind of plane. And from here, you're going to be able to identify what is the velocity of these particles in that specific plane. And once you have that, what you will be trying to do is from these two sparse of velocity observations, you will be trying to reconstruct the full velocity and the full pressure field. Okay, as before, you identify the target problem, you identify the closest problem, you identify the corresponding method, you generate your action space, you sample from here, and then you define your method. In this case, also the agents take care of all the pre-processing of the data. And here, the interesting part is not only that before even solving it, they identify that this is an ill-posed problem. An ill-posed problem is a problem that doesn't have a unique solution. So they can give you an answer, but you don't know if that's going to be the right answer, right? So in this case, it says that there's information that you're missing, that if you only have information on the middle of the plane. But it interacts with the user and then it asks if I know everything, something on top, and then it can identify that it can, using an additional constraint, can move it from ill-posed to conditionally posed. And these are how the results look like. Sorry, I forgot to clean my drawings. These are how the results look like. And again, you go from this to the sparse velocity to the full field. And this is an inverse problem. Oh, by the way, this paper that I'm just showing you right now, this was published in PNAS like a few years ago. Okay. Now, maybe another part that is interesting is like how these agents can be used to discover new architectures in some sense. And this discovery for now is mainly done in the formalization group. And the idea is like you will have a team of agents that are going to interact with the user to define a problem in a better way. And why do we need that? And it's because going to the part that Athena or these agentic systems, right, they are trying to be a map between problems and methods. So the problem has to be well defined, has to be described properly and in the best ways, in the best possible way, if you want to get the best possible method. In this case, you have an agent that tries to formalize what the user is saying. For example, the user say, okay, have this equation, or I don't know what equation works for this problem, or things like that. Once it's identified the PD and the boundary conditions, then you will have another set of agents that are going to try to simplify the problem. They're going to try to find if the problem has some kind of exact solutions, as we saw it with the implicit barriers in 2D, or if it can be simplified in any way to, for example, try to get some kind of dimensionality reduction or reducing the PDE order and other type of simplifications. Once the first agent, which in this case this codex, will generate some options, you will have a Claude trying to identify which one of those options is the most suitable. Once they agree into that, they will try to derive it to prove that this works. And then you will have a well-posedness analysis from another agent that makes sure that this problem can actually be solved in a suitable way. And maybe the thing that when they interact, one thing that they figured out was that you can express the solution for this, in this case was for viscous barriers, as a sum, as a Fourier expansions. And instead of learning U directly, what we can try to learn is the coefficients. And they complain at the beginning that they think that they should not be doable, and then they agree. They agree with each other to use it, and then they try to solve the problem. But maybe the general idea here is like, instead of solving the U directly as you would do it with a normal ping, you'll have your X component, your spatial coordinate, you send it to a Fourier expansion, and the time you send it to an MLP. The MLP gives you the coefficients. Once you have the coefficients and the expansions, you can reconstruct your solutions. And then once you have that, you construct the nonlinear term by projecting them back into this Fourier space. And for the time-dependent derivative, you can use normal automatic differentiation, and then you construct your Galerkin residual, and then you just minimize it like normally. Um, Something interesting here is that, of course, this problem will require new things that did not exist in your action space. So, but that's the flexibility of Graft. So for example, in this case, you see that the initial tree only contain like 156 cells, but to solve this problem in that way, you need a few more, but they can be easily adapted, included into the action space. So, and then this will become knowledge for the next iterations. This is the target problem. This is the predictions. These are the solutions. And maybe one of the things that we can see here is like that it has some exponential convergence. And this is somehow interesting because we never know when we're into the MLP, right? We never know how many neurons should we use, what would be the size of the last layer. But with this architecture, essentially, that thing is completely correlated to the performance that you will get. And the agents have some insights about that. For example, when they were in the first attempt, they used only 48 nodes, which would be somewhere around here. And then they figured out that the error was quite bad and then the loss was flat. And then they identified that this does not mean that this is not training a stagnation, but it means that it's some kind of a spectral deficiency. So they asked to duplicate the number of nodes, of elements, and then you can get this exponential convergence, which, yeah. And I think I'm right on time. So maybe I'll just finish with this slide on what worked and why. Maybe one of the interesting things is like into the Apollo mission, like why it works so well and why it works so fast. Because the tree contained the documentation from Trixie and the documentation from a spectral element. So the information was organized into this tree. So it was a good, well-written documentation. So the system could identify it from there. The ping benchmarks get to near machine precision, and the reason is because they have a strong optimization, as well as adaptive weighting uh, that is composed naturally into the action space. And maybe this is maybe something that I want to re-emphasize, that everything is on how you construct the graph, and this graph is constructed by interacting with experts. So this graph has this ability to extract or store expert information, and that's why it can perform so well, because it's building on top of experts' information. Or in the ping benchmarks, strong optimization, but adaptive weighting. Yeah. In the again, they got really good performance for the in vivo inverse problem. Again, because they have like a really good framework, which is they have like this negative log likelihood. This has BRBA, so adaptive activations and other tricks in that they already live in the action space and the closest problems were already solved with that. So they just have to take them and then improve them. So improve them in a reasonable way. Yeah. So it's not like they are just repeating, because, for example, if you see, they beat all the humans, right? Because they have this refinement, but this refinement is not done random. It's done in a structure because they have the information. They have the way how humans think about the systems. Um, yeah, spectral ping exponential convergence. Again, they did it because they have like a really strong second order optimizer. So they did it because the optimization error was small enough such that the representation error could be the greatest one. Yeah, this again, this system that I just mentioned is still an L2, a level 2 memory. Is like still an intervention level. It's not counterfactual. However, the main idea was like to try to construct something that takes us into that direction. And one way to try to encode counterfactual knowledge was like by including the experts' information, because we have the knowledge, we have no notion of causality. And also the graft already give us some kind of nice structure where we can try to use counterfactual learning, counterfactual techniques. Um, Yeah, and maybe an acknowledgement to my group, to my advisor, Professor George, for branch group at Brown, and also my collaborator, Jiaoji, who worked mainly on the on the DPD part, and maybe Danny for the Athena paper, the first Athena paper. He worked a lot on the textual bandit, and the NH, which is the one who funded my research. Thank you everyone for your time, and I'm happy to take any questions if you may have any.
Hey, thank you so much. I have a question. Maybe that's basic, but I just wanted to ask, how do you decide which agent do you use for each step of the work? I mean, you have different options, I guess, but
Yeah,
uh,
it's basically on the restraints. For instance, like Codex, it's quite creative, but it's a bit not that careful. And for example, Claude is really good at coding, but also is a bit more precise. So, for example, in this case, when you try to ask it to simplify the problem, to get simplifications, to get all other options, you want an agent that is creative. So, and then, but you want to have someone who controls it, who is kind of like a bit more strict.
so
And in this case,
do you
yeah,
just decide that manually based on your experience, or you have some system that the system itself can decide which of them is better at each stage?
no, in this case, I did it manually, and the idea that Codex is creative, it's kind of well known in some sense, like, and if you play with it, yeah,
Okay. Yeah, that
yeah,
would be
and also,
great. That would be
and
because I'm just asking this because I personally I was struggling which one to use for which purpose. And yeah, that was the reason I was asking. So if you can just share which of them is better for which, that would be
yeah,
great.
of course, yeah. So ChatGPT is really good at creative stuff, like, but his proofs especially can be a bit sloppy. So
Mhm.
Claude is quite a bit way more precise, and it works is better at following instructions and for coding for things that are like a bit more controlled. They are way better. And in this case, we also have like Gemini, and maybe Gemini is quite good because it's really good at managing like a lot of information. So all these systems have a thing that is this agentic system have a thing that is some kind of like a context degradation, which means as you give them more information, the performance start to deteriorate. And for Gemini, this degradation is a bit farther away. So you can feed more information before they start to hallucinate. So that's kind of like the three things. So Codex for creativity, Claude by reliability, and Gemini when you have a lot of information that you want. So they're really good at summarizing things, but they're not that good at making connections. Yeah, I don't know if that helps.
Right. Yeah, that was great. Just one last small question. So do you
Yeah.
create a kind of shared memory between them and they automatically share the information between each other?
Oh no, no, no. Each one of them have some kind of like a specific tasks. The only ones that have access to this global memory, which is what we have here in B, is,
Mhm.
for example, in the strategy team when they are trying to sample stuff to make sure that the what they are selecting from this action space is consistent, and also when they try to encode it. But they only get access to that specific part of the memory. So if you try to give them to make them all of them share the same information, you would fall into the problem of the context degradation that I just mentioned a few seconds ago. So they will start to fail.
Yeah. Thank you so much.
So thank you for your question.
Hi, Juan. Thanks for your great presentations. I also have a question. Does the human experts work as a role of the prior knowledge, or do they also work to provide the information as strategy teams or the advisor teams?
Well, you can do both. In the example that I just showed, the human did not interact with the system, but you could, like, for example, here you could you see that this user has an Claude that is using it as a gate to all the other stages, right? So for complex problems, maybe for simple problems, maybe you will trust the agents and you would just let it run for a couple of hours and come back to see the result. But if it's something completely new, and then you can actually identify it when you do this, for example, when you have like this Hakar distance, if this Hakar distance, which is the similarity of the previous problems on the memory, is too low, well, essentially means that it's highly likely that they may mess up. So maybe there you want to pay to spend more time trying to figure out that what they are doing makes sense.
So it just like something we works with the cloud or the like codecs to do with the interactions during this process.
Yeah. Thank you, Joe.
It seems Sean also has a question.
Hi Juan, great presentation. But before my question, I think there's one question in the chat box. I'll read that
Oh,
for you.
okay.
Yeah.
Thank you.
Akash asked you, can you share insights on how coding agents like Cloud and Codex interact with each other? Yeah, you can finish the remaining part. Yeah.
Oh, okay. Thank you, Akash, and thank you for pointing out the question, Juan, and also thank you, Akash, for your question. The answer is like yes. You don't ask them to interact with each other as per se. You ask them to modify the code. So you will have to, for example, in this case, or Athena has installed Nectar into their system, and it has installed. In this case, we have like thing they're called Navlas which is a library for scientific machine learning, and it has Trixie, and then they write the code. So the way they interact is just through MD files and through the modifications in the code directly. So yeah, so just by reading the log, so just MD files, markdown files.
Okay. Oh, so you're actually okay. I guess I want to ask my first question. On your
Yes.
page 14, you said you can merge the strategies together.
Yes.
So after merging that, you actually just write a new script and then feed that script to the solver or something, and then that will solve the problem, and then you can take a look at the errors, or
Oh,
it's a conversion fee.
Actually, maybe we can take a look at here, right? So once you find the closest problems, each problem will have an associated method, and then these methods will live in this kind of like nice space, right? So since they live in this common space, you can average them. So you can just, for example, let's assume that this thing you can just maybe here you can just assign a weight based on the distance. Let's say you can use, for example, where we use is the reward times the closeness, right? For example, you can do 0.4 of this term plus 0.45 of this term plus 0.6 of this term, and then you renormalize it. So then, for example, this element somewhere around here will appear here as as kind of like a dot. So you don't merge the code itself. What you merge is exactly what you're looking at here. These three things.
Yeah. So are you merging the the solution you have already together, or you just merge the methods together? You merge the
Oh,
methods together.
Just the strategy. What we merge is the strategy to solve the problem. For instance, this may be, I don't know, like second order optimizer. So this is telling you second order optimizer, this second order optimizer. So this is darker. So when you have this action space, you will have another agent that will come here, and then he will read this thing. And when he goes to the optimizer, he would say, okay, I have to choose Adam or SS Broyden. And he will see, okay, Adam has 20% of probability. This one has 60%. Okay, so I'm gonna choose the one with higher probability. And then once you define your plan, you write your code based on that plan. Does that make sense?
Yeah, that makes sense. So basically, after merging those methods together, you will create a script, and that script will run like a linear solver or something to solve the problem, or you just run a like ping-based method or some scientific machine learning method to solve the problem.
Yes. So once you maybe when we go here, let me clear this thing. So once we are here, here. Once we are here, we merge them in this way, right? So the dark color is higher probability, lower probability. Then we use an strategy team that will go section by section and is going to sample one option from all of them. And then, for example, you see the method is just the darker color. So once you have this method, you send it to the implementation team, and then the implementation team will try to code it in whatever language. It could be like a linear solver, it could be pings, it could be an operator, or whatever so they're going to write it again.
I see.
So they will write it here from scratch in some sense. They will take it from scratch.
Could you please remind me again the platform you used for merging those agents together? Because I'm very interested in that.
Oh, I don't ask them to. I don't merge them. So I have an instantiation of codings and an instantiation of Cloud Code, and the way that they interact, if I need to make them interact, is in a Bash script. So
Oh, I
so
see.
just
Got it.
yeah.
Got it. Got it.
Yeah,
Okay.
but
Thank
I
you.
believe you could use something like LangGraph. Actually, the first Athena that was written in with LangGraph and LangChain, you could use that, I guess. Yeah.
Yeah, that makes sense. Recently I heard open cloud was really popular. Have you considered the yet?
I think that OpenClaw it's important. It's like it has like the tools, right? But for example, at least from my experience, I feel like nothing that OpenClaw can do that Cloud Code cannot do directly. So if I can do it directly with Cloud Code, I didn't use OpenClaw. But because that's the only difference. So it's actually in OpenClaw you use the brain of OpenClaw will be either ChatGPT or Claude or Gemini. So I can use the agentic tools directly from Claude.
I see. Got it. Thank you.
Okay, thank you so much, Sean.
Thanks, Juan. I have a follow-up questions from Shen. I want to ask, do you have a reasoning layers in the graph to select or to explain why the proposed method is better than the others?
Oh, how can you repeat? So if I have a way to identify how a proposed method is better than the others?
Yes.
Oh, yeah. So actually, maybe that's my fault because I made it like a bit disconnected. But if we go here, every time that you have a method, every time that you analyze it, you assign it a reward. And this reward will be related to things that are related to the problem. For example, in pings, maybe you want to consider the loss. Maybe in numerical methods, you want to consider the convergence, or maybe the time that it takes to solve it, and the number of elements that you use, and things like that. So in other words, here in this stage where, sorry about that. So when you go to the advisor, you see that the advisor generates this RI, which is the reward. And this reward will be based in some kind of a specific metrics. For pings, it's just the loss. And it's also for instance, if you have oscillations, or if your boundaries are captured properly, if your loss is not flat, and things like that, like normal heuristics that people use to refine methods.
Gotcha. Thank you so much. Does
Thank
anyone
you.
has any further questions? Well, I will continue to ask some general questions. Please feel free to jump in if you have a specific question you want to ask. So for the first questions, I would like to ask you to share your experience as a graduate student at Brown Universities. How does it been so far?
I really like it. This is a really nice place. George is really he lets you play work on things. You will have some base projects that you have to do for your fun, but you have other projects that you do for fun. So I really like this place, I guess. Yeah.
Would it be too mathematics very hard to study or work with?
Can you repeat that question, please?
For the project you are working, would it be too mathematics? Like you need to derive a lot of things and think about the algorithms and try to find what best.
I think that it would be like a mix of both. Like, yeah, I think that especially in our group, we use math quite a lot, but yeah, but we're like from applied math, so we use it a lot, but we just prove things when the things that we do, but we don't go that much into depth. Yeah.
I noticed that George maintain a very large group. How does it feel in such a large group?
Oh yeah, it's indeed quite large. We're like 35 people here. It's like we have like 10 PhD students and like 25 postdocs. But it's really nice because there's a lot of people working with several different backgrounds. So when you have a question, there's always someone in the lab who may know something or have worked in something similar. So it's quite cool, or at least I like it.
Yeah, that's very impressive. And do you have any advice to provide to the current or prospective graduate student in computation methods?
Um, yeah, maybe one advice would be like all these agentic systems and all these codes and all this ChatGPT help a lot, but I think that you people we should still keep studying and keep thinking from our side. Because maybe in this graph these graphs show you like these LMs will be able to give you like really good performance if you have some kind of background to guide them. If not, they will not. So yeah, maybe that.
Thank you so much. And I have one last question. Do you envision this graph framework as a specific framework for the numerical methods, or do you think it is a more general framework for the scientific discovery?
It's a bit more general, and if we go to the motivation one, it's like with this toy example about the day, is like when you have an agent and you're asking to solve problems, then a natural way of describing the thing is by defining its categories and then specific characteristics in each one of those categories. And what you're always trying to look is kind of somehow this map, and then we show it, right? For example, we show it for several different families, for analytical things, for this DPD. In this case, I'm just showing PDs because that's the only thing that I know how to do, but I believe that this could be extended to other fields too.
Yeah, it sounds very powerful. And thanks so much for your sharings. Does anyone has any questions? Well, we will end this seminar today, and thank you again. And at last, I will send you a follow emails, and we will send you a gift to you for these presentations. Feel free to share your address with us.
Oh, thank you so much, Aaron. Thank you so much, everyone, for your time, and I really enjoyed this. Okay, bye, everyone.
Bye.